When we irrigate, we want to ensure enough available water in the soil for plant consumption. As we learned in the first video in this series, before we irrigate, we need to calculate the required amount of water. But we still face some other challenges when planning our irrigation. How long will the water be available for efficient plant consumption without stress? And how can we avoid over-irrigation that can result in water waste or even crop damage? The answers are connected to soil type. Take a look at these 3 cotton fields. In all 3, the crops are at the same development stage, have the same environmental conditions, and therefore the same water requirements. Even though they get the same overall quantity of water, in each field, the crops develop differently. Why? The answer is in the soil. Plants use their roots to consume water, air, and nutrients from the soil. Soil is the plant's water bank, or in other words, all the water that plants consume is held in the soil. Soil has 3 main components: soil particles, organic matter, and pores or voids containing changing amounts of water and air. The key parameter for classifying soil is particle size. There are 3 main soil particle types that vary in size: sand, silt, and clay. Particle size affects the size and quantity of pores. Between clay particles, there are many small pores. Between sand particles, there are fewer but larger pores. In a given volume of soil, the overall volume of pores between clay particles will be bigger than in between sand particles. Soil with a high percentage of sand is called light soil. Soil with a high percentage of clay is called heavy soil, and soils in between are called medium soils. Each field has a different soil texture with different combinations of sand, silt, and clay particles. To classify soils, we use the common FAO classification. This includes 12 soil types represented in the soil type triangle. At the edge of the triangle, we see the 3 basic soil types, and in the middle, their different combinations. If you don't know which soil type your field has, you can run a soil texture analysis with your local certified soil lab. Remember our cotton fields that were equally irrigated but developed differently? According to the lab report, each field has a different soil type. Field 1 has loamy sand, which is a light soil. Field 2 has clay, which is a heavy soil. And Field 3 has a silt loam, which is a medium soil. When all other conditions are equal, soil type has the greatest effect on crop development. But what is it in the soil that affects the plants? It's mainly the water in the soil. Soil has a capacity to hold water, and with each soil type, the capacity varies, since each soil type can hold different amounts of water. We call this water holding capacity. Soil type also has a strong effect on water dynamics in the soil. The water dynamics refer to water distribution and content. Water distribution in soil is mainly due to the downward force of gravity. Water also moves in all directions through very small spaces from wetter to drier areas by capillary movement. Look at these 3 soil profiles. Although they are all irrigated equally, the pattern of water distribution is different in each one. In the light soils, water distribution is typically in a narrow conical shape because of the large particles and fewer yet larger pores. Water distribution favors gravity forces over capillarity. In the heavy soil, water distribution is typically spherical in shape because of small particles and many fine pores. Gravity and capillary forces are affecting water movement more evenly. This means for the same amount of water, we see different wetted areas in different soil types. Now, we've got all the basics straight. Let's talk about how to put this into action. Soil water content is the amount of water in the soil at any given moment. The dynamics of soil water content is affected by several factors: water movement, plant consumption, evaporation, and rain or irrigation. There are 3 well-defined levels of soil water content. Take a look at this soil profile. After rain or heavy irrigation, the soil becomes saturated with water. The soil water content is at saturation state. This occurs when all pores in the soil are filled with water. When irrigating, we need to avoid the saturation state, as plant roots need air as well as water. Soil water content starts decreasing mainly because of gravitational drainage. At a certain point, the soil water content reaches field capacity state. Field capacity occurs when the upper limit of water that the soil can hold after drainage is reached. In this state, soil contains both water and air in the pores. As soil water content continues decreasing, mostly from plant consumption, it reaches wilting point. In this state, soil contains the minimum amount of water required for plant survival. Below wilting point, plants cannot survive, and crop wilting is irreversible. The volume of available water for the plant is between field capacity and wilting point. The range is defined as total available water, or TAW for short. The optimal soil water content to keep plants healthy and productive is field capacity. As we know, water is dynamic. Nevertheless, we need to keep it around field capacity to avoid the wilting point. Therefore, we need to define a threshold within the total available water that will indicate the minimum amount of water in the soil. This is called depletion threshold. Depletion threshold changes according to the crop's demands and its developmental stage. If we don't have a specific value, allowable depletion usually ranges from 30 to 50%. The range within field capacity and the depletion threshold is called readily available water, or RAW for short. RAW is the available water in soil that can be easily extracted by plants. As we learned, the heavier the soil is, the more available water it will contain. This is correct for all soil types, except soils with a relatively high percentage of clay. Clay particles hold some of the water very tightly, such that it is not available for plants, meaning the volume of available water in clay is not the highest. Now, back to the cotton fields. The RAW in each field is different, since each has a different soil type. So how can we control and maintain the optimal soil water content in all fields? We can achieve this by applying water in a way that maintains water content always between field capacity and the soil's depletion threshold. This will be determined by the frequency of irrigation events and their respective volume. To gain a better understanding of irrigation scheduling, watch our next video, Irrigation Scheduling. Thanks for watching.